Okay, so in section 1710, I'm going to talk about going faster than the speed of sound, so going supersonic, and then also talk about shock waves. So I'm actually going to pull up Wikipedia, which has a pretty good graphic about this. And so what I'm showing here on the very left-hand side is sound waves being emitted from a source that is stationary, so it's not moving. But then we start to move the source, like we talked about in the previous section with the Doppler effect. And what you can see in the next graphic over, that the source is moving, that little red dot, and so the wavelength observed is starting to get shorter and shorter because the source is basically moving into the sound. And on the left-hand side, the wavelengths are starting to get wider and wider. That's what we used to calculate what the Doppler effect was. But the interesting thing is that now you can actually calculate what the frequency is going to be with the Doppler effect if you're going at the speed of sound. So the source is now moving at the speed of sound. And so what you have then is that dot is now riding on the very edge of those circles, the wave fronts that are coming out. And so, and then finally, what you can do is think of going faster than the speed of sound. So you're in a jet airplane that's going at speeds greater than the speed of sound. Now that little red dot is going to be in front of the sound. So the jet is actually moving faster than the sound can catch up to it. And so you get this interesting cone, what's called the Mach cone, of these circles that are piling up just after the moving jet. Okay, so let's take a look at that. First, let's take a look at the case of, let's say the source. So V source is moving at the speed of sound. So our measured frequency, we said, was the speed of sound divided by the speed of sound minus Vs. Let's say if it's moving towards the detector. And so if that is the case, then what we get is basically something that is undefined. So basically at that point, we're not going to hear it. We're not going to measure a frequency that's audible if we're looking right up at that jet airplane. We're only going to get the sound after the airplane has passed by, and after the sound has a chance to kind of slow down or go to a lower frequency. Once you go supersonic, then things get kind of weird, because the plane is moving much faster than the sound itself. So really what happens is there's a delay. You look up in the sky and you hear the sound, but then the plane is no longer right where the sound should be. The plane is now gone past where our ears think the sound is coming from. So that's also why you get this sonic boom. You get this large cracking sound when the plane has now burst past the air and is now going faster, and there's now sound has to build up behind that plane. So we can actually calculate what's called this this Mach cone, where here's the source, which is now moving with the speed faster than the speed of sound. And it's now left behind it this trail of circles, which is going to be very, very hard for me to draw. So I would recommend looking in the textbook. But in the end, what you have is you can actually calculate from the speed basically an angle theta right in here, to show you which kind of represents how fast the source is going and how fast the sound waves can expand out. So it turns out that the sine of this angle, if we do some geometry, looks like the speed of sound divided by the speed of the source will give you the shape of that cone. So we can quantify now how fast it's going by what's called the Mach number. And you can get it from the ratio, not of this will give you a fraction, but if you flipped it over, so our Mach number would be basically this ratio of how fast the source is going to the speed of sound.